All right, so I'm going to do a little refresher on complex numbers here. However, I am going to assume that you are familiar with them already to some degree. Just going to talk about the stuff you probably wouldn't have covered in like high school algebra. So real quick, complex numbers, we're talking about numbers like x plus iy, where this is a real number, that's a real number. This one has a special name, it's called the real part of z. This one has a special name, it's the imaginary part of z. And then I is the square root of -1. It's defined to be that way, right? So that way that whenever we take square roots of numbers, we don't have to worry about it not existing. We can always just define it to exist using I. So we represent complex numbers by a point in the plane where this is our x-axis, and if you like, this is our imaginary axis. And then you find x here, you find y on this, and then this point is x plus iy. And you can draw a little triangle, little right triangle, and it's just like points in the plane x and y, you know, except you have it written like this. Okay, so there's a second way, if you don't already know, to write complex numbers. This is called the Cartesian or rectangular form. Because we're forming like this grid just like we normally would in Cartesian coordinates. But there's another way, and that is to look at this length, this distance from the origin, and this angle it makes with the x-axis. We'll call it theta, and we'll call this r. So if you don't know this already, you can describe the plane in polar coordinates, actually a bunch of different coordinate systems, other than just the normal grid. And what this means for complex numbers is that you can write every z like this. You can also write it as r times e to the I theta. Now where's this e to the I theta business coming from? Well, it comes from Euler's formula, which says e to the I theta is equal to cosine theta plus I sine theta. If you've never seen this or heard of this before, don't worry about it too much. Just realize that the unit circle in the complex plane, so x, I, y, this is I, this is negative I, this is -1, this is +1, right? This unit circle can be, at any point on this unit circle can be written as e to the I theta, where this theta is the angle. Just have to take that for granted. It's actually a really beautiful statement, but it involves some calculus to sort of show that it's true. So I don't want to get into that, but you can just take my word for it that that's possible. And then the r out front is just going to be a real number, a positive real number, and it's going to tell you what the length is, right? So you can imagine concentric circles and picking a point out by how far away it is from the origin, right? The radius r and this angle. And you just write it r times e to the I theta. And that works. And e, if you really don't know, if you haven't seen e, e is just 2.718 blah, 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 blah. It's just an important number, and you can raise it to a power. I know this is a lot, but I'm counting on most of this being reviewed, except for maybe the polar form. So, yeah. All right, now taking powers of complex numbers. Suppose I want to take z to the power n. N is a positive integer. Well, we could write x plus iy to the n, and this is just, you know, x plus iy times x plus iy, blah, 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 n times. But that would be really tiring, and we really don't want to do that. So let's instead write z in the polar form, r e to the I theta to the n, and then we use the cool property that is exponents. This turns out to be just r to the n times e to the I theta to the n, and then this is just going to be e to the I n theta. You multiply exponents, equals r to the n times e to the I n theta. This whole business right here, it's called De Moivre's theorem. I don't know if I'm actually saying that right, but I don't also care. Let's talk about the nth roots of unity. So, if we want to take the nth root of the number 1, You'll recall by the fundamental theorem of algebra that this equation in general has n different roots. So n different numbers, which when raised to the nth power, are going to give you 1. All right, so how do we find these? Okay, obviously one of them is 1, and we know that any number on the unit circle in the complex plane can be written as e to the I theta. And I'd like to point something out here. The number r, I said you could write z equals r e to the I theta for any complex number. R has to be 1, because if it's not, remember by de Moivre, or whatever that is, z to the n is equal to r to the n times e to the I n theta, so that it's going to be further than 1 away from the origin when you take the nth power of it, if r is not 1 to begin with, or if r is greater than 1. If r is less than 1, then it won't be 1 when you take it to the nth power. So the point is, you want it to stay on that unit circle. All n roots, all n nth roots of the number 1 have to be somewhere on this unit circle. Okay, so that being said, we know r is equal to 1, so we can just write z to the n is equal to I n theta. Now, something you might notice, so I said that you could write any number on this circle as e to the I theta. Well, for the number 1, theta is just equal to 0. But that's not the best way to write it, perhaps. If you go around once, that's a rotation by 2 pi radians, 360 degrees, but we use radians. So that we could also write it, in addition to e to the I times 0, we could also write it as e to the 2 pi times I. That's equal to the number 1. All right, so if we want a number which, when you take the nth power of it, is equal to e to the 2 pi I, we just set these two things equal, and then look at the angles, right? So what we want is for n times theta to be equal to 2 pi. Or, even better, it could be any multiple of 2 pi. It doesn't have to be 1 times 2 pi, because it doesn't matter how many times you go around the circle. If you end there, then that's the number 1. So we'll just put 2 pi k for any integer k. Divide by n, and you get theta is equal to 2 pi k over n. And as k, so k is equal to 1, 2, 3, etc. But you'll notice this will repeat after n different values. And indeed, we will get exactly n different numbers out of this. So that our n different roots, it'll actually make a regular polygon on this, which is a cute thing that we could talk about another time. All kinds of cool stuff with complex numbers and geometry. Lots of connections there. But our n numbers, which to the nth power are 1, are going to be e to the 2 pi I times k all over n, for k equals 1, 2, all the way up to n. These are called the nth roots of unity. And specifically, for k equals 1, just the basic one, you could also write it like this, right? Because of the way exponents work. So this particular one, e to the 2 pi I over n, is called the primitive nth root of unity. And we're just going to denote that from now on as omega sub n. And you'll notice all the roots of unity can be written as omega sub n to the power k, for k is 1 to n, one of those values. Okay, so nth roots of unity, these are going to allow us to take roots super easily. Let me show you. All right, nth roots of unity, these are going to allow us to take roots super easily. So if I want the nth root of the number z, a complex number, it's going to be equal to r to the 1 over n, taken in the positive and real sense. We want the positive root there, times e to the I n, or I theta, over n, and this is going to be sort of the primitive root, and then we're going to take the primitive root of unity for that, right, remember, which is e to the 2 pi I over n, and it's going to be to the power k, and there will be there will be n different roots, n different nth roots of the number z. So nth root of z is going to be any number in this set of r to the 1 over n e to the I theta over n, r to the 1 over n e to the I theta over n times omega n, r to the 1 over n e to the I theta over n times omega n squared, all the way up to r to the 1 over n e to the I theta over n times omega n to the n minus 1 power. These are going to be your n different nth roots of the complex number z. All right, so this is all we need in order to solve cubics. It may, depending on your background, this may seem like extremely little or a lot. So, but just knowing how to take the nth power and the nth root of a complex number is going to get us to solving cubics. Because if you recall by the fundamental theorem of algebra, it guarantees that a cubic equation has 3 solutions, but it doesn't guarantee that they're all real numbers, right? They might have these imaginary bits, so we have to be able to deal with complex numbers. All right, so without further ado, cubic equations.